We introduce cervical spine range of motion measurement utilizing image analysis, a system that measures cervical spine range of motion angles. First, I introduce about serum definition. The cervical spine is composed of 7 vertebrae. The cervical spine range of motion are the difference in each angle between C1 and C7 into X-ray images. CROM is an abbreviation for cervical spine range of motion. We call the cervical spine range of motion CROM. I explain how to measure CROM angle by physicians. Firstly, they take X-ray images of flexed and extended cervical regions. Then draw lines as shown in the image below, like this. Finally, they calculate the angle differences for each pair of lines between flexion image and extension image. Measurement purpose is analyzing the mobility between vertebrae from cervical X-ray images. Physicians use CROM as a basis for making diagnosis decisions. I explain why I study this work. There are 3 reasons. The first reason, the cervical spine is one of the areas on which many imaging studies have been focused. The second reason, CROM measurement using X-ray images is burdensome for physicians. The third reason, physicians may be asked to perform diagnostic imaging in areas in which they do not specialize because of lack of physicians. Next, I introduce related works. This work used the mask RCNN and UNET to extract lung regions from chest X-ray images. This study found that while UNET is more accurate in terms of extraction accuracy, mask RCNN is more robust to the diversity caused by change in the shading of X-ray images and changes in the position of the lung due to disease. Mask RCNN has the advantage of being able to process each cervical spine section separately, since unlike other networks specialized for segmentation, it performs instant segmentation. In the present work, we extract the cervical spine regions from the cervical spine X-ray image by using mask RCNN. This study used deep learning and image processing to measure the thickness of the prevertebral soft tissue in front of the vertebral body from cervical spine X-ray image, and propose a method to diagnose swelling by referring to the flow of swelling diagnosis by physicians. We implemented a system with reference the diagnosis flow of a physician. So in this study, we aim to support physicians in measuring the CROM angles by implementing a system that automates the measurement of CROM angles from cervical spine X-ray images. Our method used deep learning to estimate the cervical spine regions from X-ray images, and our system was implemented based on the manual measurement method. Our proposed system has 2 processes, segmentation and CROM measurement. The following sections explain each of them in detail. We developed a CROM measurement system. Please look at the demonstration video. This is our application screen. Firstly, input into X-ray images into this system. Then click the measurement button. The segmentation will be started and automatically measure the serum. X-ray images, flexions, and extended cervical region need to be taken and input into the system. Both top of and bottom edge of vertebrae are marked with red lines. The next step is to calculate the angle differences from each pair of lines between the flexion image and extension image. This system can also show segmentation regions. The system proposed is shown as above figures, but I explain these processes more specifically after. First, I explain the segmentation method. We used mask RCNN. This method is one of the segmentation methods. This method can be instant segmentation. The model generates bounding boxes and segmentation masks for each instance of an object in the image. It's based on feature pyramid network and a ResNet 101 backbone. The figure shows the structure of mask RCNN used in this study. Mask RCNN architecture consists of three main layers. First, backbone extract feature of inputted images. Second, region proposer networks RPN is simply neural network that process multiple objects that are available within a particular image. The third, head identify object region candidates and region extraction. The dataset used in this study consists of 968 X-ray images of cervical spine flexion and extension in 484 individuals aged between 20 and 100 years who were participants at the Department of Radiology, Tokyo Medical and Dental University Medical Hospital. Of these 968 images, 922 were used as training data, and the remaining 46 were used as the test data. Based on the guidance of a radiologist specializing in the cervical spine mask information is created, and the pair with the original image is used as training data. The labeling is shown in the figure on the right. The regions are labeled as C1, C2, and bone. The cervical spine regions be masked a difference for C3 to C7 and C1 and C2 because of the special shape of latter. Specifically, the C1 region is an anterior arch, and the C2 region includes the entire vertebrae from the vertebral body to the otondoid process. We performed the estimation of 46 images of the test data. Out of a total of 322 cervical vertebrae in these 46 images, 313 were successfully estimated. This means that 97% of the total cost data was able to detect. Intersection over union, IOU, which is a similarity between two sets, was used to evaluate the estimated cervical lesion. The IOU value is obtained by dividing the common part of the correct and estimated regions by the union of the two regions, where the maximum value is represented by 1. The higher the value, the higher the accuracy of the object detection. The IOU value for each shown in this slides table. The mean IOU value for all 46 test data was 0.885. The IOU value of C1 and C2 were lower because these two vertebrae had less training data than from C3 to C7. Next, I explain serum angle measurement from estimated cervical lesions. The flow of the automatic annotation is shown in this figure. There are 5 steps. Step 1. The counter coordinates of the lesion are obtained from the estimated cervical lesion. Step 2. The coordinates of the convex flow are selected from the counter coordinates, and then the convex flow region is approximated as a polygon with a 3 or 4 vertices. Step 3. After this, the midpoint of each edge of the approximated polygon is calculated. The edge where the calculated midpoints are close to each other between cervical spine N and cervical spine N plus 1 is regarded as the edge of the cervical spine used for measurement. However, since approximate polygons below C3 are approximated to be inscribed in the convex flow region, their edge may be far from the contour. Coordinates of the estimated region. So step 4, we extract the contour coordinates near the selected edge in the approximate polygon. Final step, a line is drawn. These coordinates use the least squares errors method to find the edge between them. The angle between the two lines is calculated from tangent additive theory by using equation 1, where A and B are the slope of the two lines. The measurement accuracy of the automatic measurement method was evaluated by comparing the average error between the true value and the automatic measurement value, and between the true value and the reference measurement value, using the specialist measurement as the true value. The true value is the average of the 3 measurements taken by 2 medical specialists. A specialist in this context refers to a physician who specializes in diagnosis of the cervical spine, while a resident refers to a physician who does not specialize in the diagnosis of cervical spine. The data to be measured were the same 46 images of the test data used to validate the learning model in the cervical region. The true value was measured 69 times by 2 specialists, 23 persons 3 times. The frequency of measurement was limited to once a day and was not continuous. In the measurement of the serum angle in the test, the number of places where automatic measurement was possible was 133 out of 138 places for 23 persons. The remaining 5 places were not measured because the cervical region were not segmented at all. The mean error between the true value and the serum angle between each vertebra in the automatic and resident measurements is shown in this slide table. The accuracy of the proposed system was particularly poor for C1 and between C1 and C67. The mean measurement error of the proposed system and the resident was the same value, 3.5 degrees. However, the variance in error was smaller for the automatic measurement. We performed a two-side t-test at the 5% level of significance to see if there was statistically significant. This slide figure shows a comparison of the average error between the resident and automatic measurements. There was no difference in the overall means error between the automatic and resident measurements. We also calculated the standard deviation for each measurement by the specialist and the resident, with the results shown in this slide table. In the automatic measurement, the standard deviation was 0 because the same value was obtained even after 3 measurements. The experimental results show that the accuracy of the proposed system was particularly poor for C12 between C12 and C67. I think that the IOU value of C1 and C2 was smaller than those of other cervical spine regions. This fact is related, I thought. We performed a two-side t-test and the 5% level of significance to see if this was statistically significant. There was no difference in the overall mean error between the automatic and resident measurement. But we also calculate the standard deviations for each measurement by the specialist and the resident. In the automatic measurement, the standard deviation was 0. We thought that a common advantage of most computer vision methods, repeatability. We consider automatic measurement to be superior to manual measurement in this respect. Issue in the future is the accuracy of measurement was particularly poor for C12. But if we can increase the amount of training data, we should be able to improve the accuracy of the estimate of C1. Future work are to comparison as a segmentation methods, example of unit and k-means method, and develop a computer-aided diagnosis system. In the analysis of cervical X-ray measures, attention should be paid not only to serum angle but also to normal alignment of the cervical spine. We see if we can determine the cervical misalignment to estimate the defective cervical spine region, like those figures. A summary of the research is as follows. Thank you for listening.